Now, there are certain facts in calculus that seem intuitive based on what you learned, and in fact are true. Something called the increasing function theorem is one of those facts. Let's go ahead and write that down. Increasing function theorem. The increasing function theorem says if you've got a, well, intuitively, if you've got a nice function whose derivative is always positive on some interval, then the function is always increasing on that interval. And in fact, even on a slightly bigger interval. Suppose f is a function. I won't write is a function. I'll just say is continuous on some closed interval from a to b. That's notation for a closed interval. Remember where you include the endpoints. And differentiable, meaning it has a derivative on the open interval from a to b, not including the endpoints. That it could be differentiable on a bigger interval, including the endpoints. But the point of phrasing the theorem this way is we can get away with just assuming it's differentiable in the open interval. And if you can get away with it and it's still true, you may as well make the theorem as general as possible. If f prime of x is positive for all x in the open interval from a to b, the conclusion of this theorem is then f is in fact strictly increasing. I could just say increasing as well, but strictly emphasizes it's not constant at all either over certain intervals. It's strictly increasing on the entire closed interval from a to b, amazingly enough. This should make intuitive sense. If the derivative is always positive, that means tangent lines always have positive slopes. The function's got to be going up, right? As you move from left to right. I mean, what else could happen? It can't go back down again because then the derivative would be negative. Can't even be constant because then the derivative would be zero. Yes, this is a theorem. This is true. It can be proved with the mean value theorem. I'm not going to prove it. I think the book does prove it. It's a little trick using the mean value theorem. But what I want to show you is that there are related kinds of statements you could write down that sound just as true, but are actually false. A related statement, a related, and I'll even emphasize it right away here, but false statement. These are things that are worth knowing, even if you're not a math major. Most of you are not math majors. I think only a couple of you are, okay? Why? Because when you use math, probably especially statistics, on the job, it's easy to misuse it in lots of different ways. And one example of how, for example, statistics gets misused is applying various kinds of methods when they don't apply. You got to know details of when they apply. Effectively, you got to know the details of theorems, when hypotheses are satisfied, to know when you can apply various methods. It's a similar kind of thing in calculus, though maybe it doesn't come up on the job as often. Knowing details like this is relevant. Your intuition can lead you astray. What's an example of a related but false statement? In the same situation, meaning as above, meaning f is continuous on a closed interval from a to b and differentiable on an open interval from a to b. If f is strictly increasing, on, well, yeah, I guess I could say the closed interval. I could also just say the open interval I'll just say the open interval. Okay, I could say the closed interval. Then f prime of x is positive for all x in the open interval from A to B. Doesn't that sound true as well? Function's always going up. It's a nice differentiable function. The derivative's always got to be positive. Slopes of tangent lines always have to be positive. Well, that's not true.
If that is a horizontal line, then it doesn't work, right?
Well, horizontal lines are not strictly increasing. Function is going up here, always. And it's a nice function, continuous and differentiable. Okay, you might say this is mostly true. It's usually true for most examples, but there are examples where it's not. And what I'm about to write down is an example, and you might think this is a ticky-tack kind of thing. It's like, well, that's silly. But no, this one example is enough to say this statement is false. And there are true, false kinds of questions on my exams, right? Where you want to know these kinds of things. F of x equals x cubed on, for example, the interval from -1 to 1 is what's called a counterexample. It's an example that counters the thought that this statement is true, showing the statement's actually false. Now, I picked the interval from -1 to 1. I could have picked the interval from -2 to 2, or -17 to +4. The key thing is the interval's got to contain 0. Why? Because 0 is kind of the problem point. F prime of x is 3x squared, and so f prime of 0 is 3 times 0 squared is 0, and 0 is not greater than 0. But f is strictly increasing on the open interval from -1 to 1. What's going on here? Subtle details you should try to understand and realize and be informed about, including for the test. If I graph f of x equals x cubed, I hope you remember it looks about like this. There's f of x equals x cubed. The derivative is positive everywhere but 0. But at that one point, x equals 0, the derivative is 0. The tangent line is horizontal. The tangent line at this point right there is actually a horizontal line. But the function's always going up. How can this be? What's going on here? What's going on is when you zoom into this graph closer and closer to the origin, the graph looks more and more horizontal, though it never is exactly horizontal. The fact that it looks more and more horizontal is enough to say the tangent line itself is horizontal, but the function itself is never horizontal. Isn't that weird? But that's what's going on. We can illustrate it in Mathematica here. You don't need to know this code, but I'm going to do a quick plotting command here that will illustrate what's going on. Actually, let me make two graphs. Well, okay. So my original function is going to be blue, and the tangent line, or maybe I should make it like I drew with a pen here. My original function is going to be red, and the tangent line is going to be green. So here is looking at the x cubed function. And let's even try to make the window a little bit more square here. Just so you know I'm not fooling you here. Okay. So there is the x cubed function in red. The x-axis, the line y equals 0 in green. As we zoom in toward the origin, the red and green curves look more and more alike. The green line is approximating the red curve better and better. And eventually we get so close that you can't tell the difference between them. That's why the green line is the tangent line at the origin. But they are still different curves. And in fact, even though you can't tell the difference between them when you're really close to the origin, they are still different. You just can't tell at this scale. Okay? A subtle point, but it's worth making. Another example that's even weirder, I'm not going to write it down, and you actually don't need to know this for the exam, but I will show it to you in the Mathematica. Another example that's even weirder is that you can have the derivative. It's almost like the increasing function theorem. You can have the derivative be positive, but not in an interval, but instead at one point. But the function not be increasing near that one point. This is really wild. I'm going to show you a function. Let's define it here. F of x is going to equal a piecewise function. If you're interested, you can write it down, but you don't need to know it for the exam. X squared times sine of 1 over x. If x is not equal to 0. And actually, let me do something else with this. Let me add x to it at the beginning. And 0 if x is 0. That's a way to type that function into Mathematica. I'm going to plot this function along with the horizontal or the slanted line y equals x in the same picture here. Let's make them even thicker here, so it really stands out. Okay. So again, this function is equal to x plus x squared times sine of 1 over x when x is not 0, and 0 when x is 0. I have to do it piecewise if it's going to be defined everywhere, because this expression is not defined when x is 0. It's the red graph that you see. Let me make the green line actually a little less thick. Oops, that made the red graph less thick. The red graph is the function in question. What happens as we zoom in toward the origin here? Maybe we won't even be able to tell exactly, but let's just see if we can get a little feel for it. This graph, that red graph, is actually oscillating infinitely often, up and down, as you head in towards 0. Though mostly up, right? Mostly the trend of the graph is up. But there's every once in a while, there's a little dip downward, like right there, right there, right there. And that up and down motion, though you can't really tell as you get really close to the origin, is still going on infinitely often. There's infinitely many little ups and downs. You just can't tell at this scale anymore. The graph is continuous and differentiable, including at 0, and the derivative at 0 equals 1. That green line is the tangent line to the red graph at the origin. However, the red graph still oscillates infinitely often near 0. You just can't tell. If you don't believe me, you could also graph its derivative. I won't make a manipulate. I'll just make a plot of its derivative from -1 to 1. Its derivative, whoa, what in the world? Actually, maybe I should make a manipulate. Let's graph its derivative near 0. Though I have to, it looks like the y range, I have to go from 0 to 2. I'm not going to graph y equals x either, though. That's the derivative. of that function. It oscillates, it's mostly positive. It oscillates infinitely often as you approach zero. Once in a while, it goes negative. If I zoom in here, oh, it's not zooming very well. Let's see. I'm not quite sure what's going on with that zoom here. Maybe I needed to get rid of that thing. Okay, let's try this. If I zoom in near the origin, or not near the origin, but near x equals 0 for this derivative of the original function, it looks crazier and crazier. It's oscillating infinitely often, and it does go negative just barely, though you can't really tell. I made the y range closer to 0. Maybe we could tell. It still does go negative every so often. It's hard to tell, but it actually does drop below 0. Near 0, there are still little negative slopes. So what this means is the function is not increasing near 0 in a technical sense. Overall it is, but there are little tiny decreasing regions. Okay, so you don't need to know that for the exam, but it's to illustrate that weird things can happen. Just because something seems intuitive doesn't mean it's right. This is something, this red one here, is something you should know for the test. Another technicality that I want you to know about. We have the first and second derivative tests. What is that? What are they for? They're for verifying that you've got a local maximum or minimum. You can use either one test or the other in any given situation. You don't need to use both, though you should be able to use either one. You should know about them both. Technicality I want to show you is that the first derivative test is in a sense better than the second derivative test. Consider this example. F of x equals x to the fourth. You actually should know how to graph this without technology. What does its graph look like? It does look kind of like the graph of x squared. After all, it is a power function with an even positive exponent. It should look kind of like x squared, though it's not x squared, it's x to the fourth. So there are differences in the graphs. The general shape is, you might say, like a U, though it's technically not a parabola. The definition of a parabola is real technical. Actually, probably most math classes don't bother getting to the technical definition of a parabola. But if you ever wanted to learn about parabolas and details, it's not just any shape, a graph that looks like a U. It's a real precise definition. And parabolic properties of certain kinds of telescopes only happen when your telescope mirror is shaped like a parabola, or a higher dimensional version of a parabola, called a paraboloid. I think I mentioned that before, paraboloids. Yeah. Multivariable calculus. Anyway, so what does the graph look like? It still goes through these 2 points, 1, 1, and negative 1, 1, right? Because if you plug in x as 1 or negative 1, you'll get an output of 1. 1 to the fourth is 1, and negative 1 to the fourth is 1. One difference is when you plug in a number like 0.5, you get a much smaller number for the output. 0.5 squared, if you're plugging 0.5 into x squared, you get an output of 0.25. But 0.5 to the fourth power is, well, 4 times smaller. 0.0625. And it's even more extreme the closer you get to 0. If you plug in 0.1 into x squared, 1/10, you get 1/100th. But if you plug in 0.1 into x to the fourth, you get 10 to the negative 4 instead of 10 to the negative 2. 100 times smaller. 100 times closer to the x-axis for the y-coordinate. Because of that, the graph is much flatter near the origin than a parabola is. It only starts to go up quickly when you get close to 1. And then it goes up very quickly after that. And it's symmetric about the y-axis, so it's something similar over here. It's an even function. So it's flatter than x squared near the origin. Now, because this is the graph, and because x equals 0 is the only value of x that will give you an output of 0, you really do have a minimum of 0. You could call it a local minimum, you could call it a global minimum, because it doesn't get any lower. No real number x will give you a negative output here. But what do the first and second derivative tests say about this example? Well, the first derivative is 4x cubed. If you set this equal to 0 and solve for x, it's very easy. Your one critical point is x equals 0, as you would expect looking at the graph. And if you think about the sign of the first derivative on either side of the critical point, it is negative over here and positive over here. So f is decreasing over here and increasing over here, f itself. So there is definitely a minimum at 0, which we already know because we already know what the graph looks like. But it's nice to see it's confirmed with the first derivative test. However, if you try the second derivative test, f double prime of x, and plug in the critical point, the second derivative at 0 is 0, because the second derivative is 12x squared. F double prime of 0 is 12 times 0 squared is 0, not positive or negative. Get a 0 second derivative at this critical point. So what does that mean? It does mean it's not an inflection point. The second derivative does not change sign at the critical point. So it's not an inflection point, which you can tell from the graph. The graph is concave up over here. It's also concave up over here. But the second derivative being 0 means it's sort of so flat there, it's kind of not concave up at the origin. Oh, ticky-tacky stuff. Well, couldn't you still say it's concave up anyway? Yeah, kind of. In spite of the fact that f double prime of 0 is 0. But if you want to be technically correct about things, the second derivative test does not apply. You can't use it here. Because the second derivative test tells you when you've got a nice function, if the second derivative at the critical point is positive, the graph's definitely concave up near there, and you got a local min. If the second derivative is negative, the graph's concave down near the critical point, so you got a local max. You look at these examples, you should know about them. Again, for maybe true-false questions on the exam. I think on the video, I maybe consider similar kinds of questions. Okay, these are things you should know about. They seem almost just too silly to discuss. But there's really two reasons for doing it. One is, once again, to emphasize what I emphasized 10 minutes ago. Just because something sounds right doesn't mean it is. Knowing examples like this informs you about that. That's the first key thing to know about this. The second thing about this, why it's worth learning, is once again, when you get to multivariable calculus, you can't always draw pictures. And so you have to rely on the calculations and the theorems to tell you what's going on. And if the theorems do not apply, maybe it's because something really weird is going on that you can't even visualize. Okay. Things are weird in single variable calculus, they can get really weird in multivariable calculus. Okay, so it's worth learning about it in the simplest kinds of situations.